Hello everyone. In today's session, I will be looking at linear independence. I will first do a recap of the things we have learned earlier, like linear systems, vector equations, matrix equations, homogeneous linear systems, and writing down the solution sets of the linear systems. So let's look at the topics. As I said, first we're going to have a recap of the concepts we have learned earlier. And then I'm going to start with linearly independent and linearly dependent sets. Then how can we look at the linear dependent relation among the linearly dependent sets of vectors, and some characterization of linearly dependent sets. So let's look at some recaps. First, we're going to talk about the spanning set of vectors. So if we have a set of vectors in Rn, say V1 Vp, then when we gather up all possible linear combinations of these vectors V1 Vp and put them together in a set, that set is called the spanning set of the vectors V1 Vp. Now, this spanning set of vectors is also called the span of set of vectors, is also called the subset of Rn, which is spanned by the vectors V1 Vp. Another way we can also say the span of the vectors V1 Vp is the collection of all vectors, which can be written in the form of C1v1 plus C2v2 plus ... CpVp with the scalars C1 to Cp. Okay. As we have discussed many times earlier, the relationship between matrix equation, vector equation, and linear systems. If A is a m by n matrix with columns A1 to An, and if B is an Rn, then the matrix equation Ax equals to B will have the same solution set as the vector equation x1a1 plus x2a2 plus ... plus xn an equals b, which in turn says that the solution set of the system of linear equations whose augment matrix is given by this will have the same solution set, a1, a2, an to b. So this equation Ax equal to b has a solution if and only if b is a linear combination of the columns of A. So let's go over to homogeneous linear systems. A system of linear equations is said to be homogeneous if it can be written in the form of Ax equals 0. Now remember, a linear equation can be written as a matrix equation. So I'm writing the system of linear equations as a matrix equation, where A is a m by n matrix and Z is a zero vector in Rm. By the virtue of its definition, every homogeneous linear system is consistent. And that solution, which makes it consistent, is the trivial solution. And that trivial solution basically means the zero vector. Because when you plug in Ax equal to 0, notice this one. Ax equal to 0, when x is 0, by default, the homogeneous equation is going to have a solution. Okay, now continuing on this definition, continuing on the homogeneous linear system and the trivial solution of a homogeneous linear system, we are now going to look at it from a different angle. Instead of looking at the vector, the xi's, we're going to now look at as in terms of vectors and play more importance to the vectors. So let's look at it. Now, if a homogeneous linear system has a trivial solution, that is the corresponding matrix equation Ax equal to 0, if and only if all the xi's are 0 for I from 1 to n. In other words, when you write this matrix A, suppose it has columns A1, A2, say An, because matrix product has to be valid. And this is the vector x1, x2, xn. So if the homogeneous linear system or the homogeneous matrix equation has a trivial solution, that is this matrix equation Ax equal to 0 and will only have the solution given by the 0 vector, which is xi's are 0 for all i's 1 to n. Now when we write this matrix equation as a vector equation, that means we can write this matrix equation which is written above as a1 x1 plus a2 x2 plus a and xn equal to 0. Now remember the ai's, a1, a2, an, these are columns of the matrix A. So now we are going to look at this trivial solution of the homogeneous linear system as the only solution, and how we are going to say the same things but in a different form. So if a vector equation, so look at this one, if a vector equation given by 1 has only the xi's to be 0 for every I, then the set of vectors that is formed by the columns of the matrix A given by a1 to an is said to be linearly independent. So in other words, if I have a vector equation a1, x1, an, xn, where the xi's are scalars, and the only way this vector equation is true when xi's are 0, then the set of vectors, which are basically the columns of the matrix A, which is given by a1 to an, is said to be linearly independent. Remember, we started with a matrix equation having only a trivial solution, and we have just changed it and looking at it from a different angle. Instead of looking at the matrix equation, we're looking at it as vectors. We're looking in terms of the vectors. How does it affect the vectors? Okay, so this is like looking at homogeneous linear system trivial solution have a homogeneous linear system having only a trivial solution, and you are looking at it as in the form of a linearly independent set of vectors because of the virtue of its definition. Another way to define a linear independence is this. If you're given an index set of vectors v1 to vp, we say that they are linearly independent if the vector equation c1 v1 plus c2 v2 dot 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 plus cp vp equals 0 has only the trivial solution. That is, all the weights of this vector equation are only 0. So this is another way of saying it, that we're looking at from a homogeneous. So I started with the things we have learned earlier, that is a homogeneous linear system having only the trivial solution, and just focus more on the vectors part of it. And that is how we define a linear independence. And this is the formal definition of linear independence. Both are basically saying the same thing. It's just how you word them up. Okay, so we have talked about linear independence. Now it becomes easy. We can talk about linear dependence. So linear dependence, that means it is not linearly independent. How will we define it? The set v1 to vp is said to be linearly dependent, that is a set of vectors. Let's say this, the set of vectors is said to be linearly dependent if there exist weights c1 to cp, not all 0, such that this vector equation holds, that is c1 v1 plus c2 v2 dot 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 plus cp vp equals 0. So in other words, if you're given a vector equation and even one of the weights is not 0, that vector equation is telling us that these vectors which form that vector equation are linearly dependent. Okay, now let's look at how we can see the same problem in terms of homogeneous linear system. How does it define in terms of linear dependence? Okay. So Now we're focusing on a homogeneous linear system having a non-trivial solution. That is, the corresponding homogeneous equation Ax equal to 0 will have at least one of the xi's to be non-zero. Remember this vector x? Always when you're looking at the homogeneous equation, remember this as vectors a1, a2, an. And the only way a homogeneous linear system will have a non-trivial solution if one of the variables x1 to xn is not a zero vector. So when you look at the corresponding vector equation of this homogeneous linear system, it is written as a1x1 plus dot 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 an equal to 0 has at least one of the xi's for I from 1 to n to be non-zero. Then we focus more on the vectors. The set of vectors which are given by a1, a2, an is said to be linearly dependent. Remember, the set of vectors are nothing but the columns of the matrix A. So this equation 2 also gives us the linear dependence relation among the vectors a1, a2, an when the weights are not at all 0. Okay. So we have learned about the definition of linear independence and dependence in a proper form, which is given in slide 7. And also we have looked at linear independence and linear dependence in terms of the solutions of a homogeneous linear system. In a very simple way, if a homogeneous linear system has a trivial solution, then simply it means that the corresponding set of vectors are linearly independent. On the other hand, if the homogeneous linear system has a non-trivial solution, which implies that the corresponding set of vectors are linearly dependent. Straight and simple. Okay, now let's start with examples. Now we're given three vectors, v1, v2, and v3. Vector v1 is 1, 2, 3, vector v2 is 4, 5, 6, and vector v3 is 2, 1, 0. The question is, determine if these set of vectors v1, v2, v3 is linearly independent. Now, if it is linearly independent, we don't have to prove anything, but if it is linearly dependent, we would like to see what is the linear dependence relation among the vectors v1, v2, v3. Okay, let's start with the solution. Now, to find whether the vectors are linearly independent, basically, we need to know whether the vector equation made from these vectors has a trivial solution. That is, all the weights, C1 equal to C2 equal to, here it will be C3, because there are only three vectors, is equal to 0. In other words, whether the corresponding matrix that has vectors v1, v2, v3 as columns has all pivot columns. Okay, so let's look at the vector equation. Now, the vector equation is x1v1 plus x2v2 plus x3v3 equals 0. And now replace the v1, v2, v3 by the vectors which are given to us. So we have x1 times the vector v1, which is 1, 2, 3, plus x2 times the vector v2, which is 4, 5, 6, plus x3 times 2, 1, 0 equals 0. Now this is a vector equation. We can write the corresponding matrix equation. Basically, gather the vectors as columns of the matrix. So v1 is the first column, and v2 is the second column, and v3 is the third column of the corresponding matrix equation. And the weights x1, x2, x3, they will become the elements of the vector x. So this is A times x equals 0. Now, I want to find out the, whether it has linearly independent or dependent relations. Now remember, if this matrix equation has, so this is the matrix equation, it's a homogeneous linear system. And what we just said earlier, that if you have a homogeneous linear system, and if this has to have a trivial solution, the only way it can have a trivial solution is if the columns of the matrix, all the columns are pivot columns. On the other hand, if it is not every column is a pivot column, that means there is a presence of free variables, then this homogeneous linear system given by this matrix equation will have a non-trivial solution. So when you have a non-trivial solution, that means you have linear dependence among the vectors v1, v2, v3. So what you're going to do is we're going to apply the row reduction algorithm on this coefficient matrix. Okay, let's do that. Because we have to solve for, we have to see what kind of matrix it becomes. So notice, we write the corresponding coefficient matrix, apply the elementary row operations or the row reduction algorithm. So when you do this one, remember, the first thing is you have to write it in the row echelon form. That's what we have to do, just row echelon form, to know whether it will have a non-trivial solution or not, because the whole thing lies on the solution part. Is it a trivial solution or a non-trivial solution? Okay, so let's look at this one. So I hope now you are very comfortable with applying the algorithm. This one is the pivot here, and the first column is the pivot column. To write it in the row echelon form, you have to make 2 and 3 to be 0. When you apply these row operations, R2 minus 2 R1 goes to R2, R3 minus 3 R1 goes to R3. We get this new matrix. Now, it is still not in the echelon form, so you have to see which is the next pivot column. So then you go to the next non-zero row once you have got the bunch of zeros, because you have to go, you start with the leftmost column and then you keep on going till you are able to apply the, you're able to get a row echelon form. So the next pivot column is 4 minus 3 and 6. And the next pivot is minus 3. You have to get minus 6 to be 0. Apply the operation R3 minus 2. R2 goes to R3. We get this new matrix. Clearly, it has 2 pivot columns. And those 2 pivot columns means 2 basic variables. So that means it has 1 free variable. The moment it has 1 free variable, what does that tell us? This implies we have a non-trivial solution. And what did we just learn? If you have a non-trivial solution, this implies that the vectors v1, v2, and v3 are linearly dependent. That's it. So what you basically do is you write down, so in a simple form, when you're given a set of vectors, put them in a matrix form, apply the row reduction algorithm, which is basically applying the row echelon form. And when you do the row echelon form and you look at the number of basic variables, and if there is a presence of free variable, automatically it means a non-trivial solution. That means the set of vectors are linearly dependent. Okay. The next slide basically just says what I just talked about earlier. So I have 2 basic variables, x1 and x2, and every non-zero value of x3 will give us a non-trivial solution. Hence, the vectors are linearly dependent. Okay, now because these vectors are linearly dependent, that means there is a linear dependence relationship between them. We'd like to know what is the linear dependent relationship. So, and also, if because of this linear dependent, remember, it means that x1 v1 plus x2 v2 plus x3 v3 equal to 0, at least one of the xi's is non-zero. We know only that. Okay, now we have to find out what kind of relationship there is. Okay. To show this dependence relationship, once again we go and find the parametric description of the solution set of the homogeneous equation. Remember I said earlier that this parametric description of solution set is very important. We'll be seeing it again and again in different forms. Okay, so to find the parametric description of the solution set, we could have easily write the linear system of equations from here when we did the row echelon form, or we can apply more row operations and make it into a row reduced echelon form so that we have less computation. It doesn't matter, you can work from here or you can work from here. Either way you can do it. Okay, so what I've done is I have row reduced this coefficient matrix, and as I have row reduced the coefficient matrix, so this is what I'm getting. You can look over it. And once we have that, now we're going to write down the parametric description, not the vector parametric, but the parametric description. That's more than enough here. Okay. So we write the parametric description. Now, this is Ax equal to 0. We will apply the row reduced, because remember, the original matrix and the row reduced echelon form will have the same solution set. So it's better to work in the row reduced echelon form. And what do we get? When we write down the corresponding linear system, we get this set of equations. And remember, we have to write down the parametric description simply says write down the basic variables in terms of the free variables. Now, we have two basic variables, x1 and x2. These were the two basic variables, and x3 was the free variable. So we have to write down x1 and x2 in terms of x3. This is shown over here. So we say x1 is 2x3, x2 is minus x3. So given any value, say pick up any value for x3. Remember, x3 is the free variable, say it is 5. So what do we get? We get x1 to be 10, x2 to be minus 5. And this basically are three non-zero values for answers. Remember the vector is? We had the vector x1, v1 plus x2, v2 plus x3, v3 equals 0. So if I have one value of x3 to be 5, we got two values, a set of values for x1 and x2. When you plug these values in this vector equation, we get the linear dependence relationship. So here is the linear dependent relationship. And this is one of infinite many. Remember, it's all in the hands of the free variable. You change the value of the free variable, you get a new set of linear dependence relationships. Okay, now we are going to look at specific set of vectors and see what we can observe from them. Now, if you have a set of one or two vectors, suppose I have a set of one vector, so I have this vector v1. Now, if this was not a zero vector, by default, every single set of vector is always linearly independent. That's what it says. A set which has only one vector, say v or v1 here, is linearly independent if and only if v is not the zero vector. Because if v is not the zero vector, the only way, so that means, let's look at the vector equation x1, v1 to be 0. The only way this vector can be 0 if v1 is non-zero is x1 to be 0. And that automatically is the definition of a linear independence. Okay. The zero vector is always linearly dependent because you can multiply any non-zero scalar to it, it will always be a 0. Now, if you have a set of two vectors, say v1 and v2, they're linearly dependent if one is a multiple of the other. Suppose v2 was 3 times v1. Then what will happen when you write down the vector equation? So get them on one side. 3v1 minus v2 is 0. Automatically, if you look at this as a vector equation, I have non-zero weights. So what simply says is if one vector is a linear combination of the other in a set of two vectors, automatically the set of vectors are linearly dependent. So what it means in terms of linear independence, the set is linearly independent if and only if neither of the vectors is a multiple of the other. This set we are talking about, guys. Okay, let's look at another theorem, which is the characterization of linearly dependent sets. I will be only looking at the theorem, and we'll be applying this theorem to prove our results. So what is the characterization of linearly dependent sets? It says an index set S equals v1 to vp of two or more vectors. So this is the of two or more vectors is linearly dependent if and only if at least one of the vectors is a linear combination of the other. So an index set basically means you have v1, v2, v3. That means you have more than one vectors, and just index setting is like v1, v2, v3. That is it. In simple words, if you have a set of vectors which has two or more vectors, it will be linearly independent if at least one of the vectors can be written as a linear combination of the other. There's no rule that only the second vector has to be written as a combination of the first, or the third has to be written as a combination of the first two. No, it's a very general form. In fact, also further, if S is linearly dependent and one of the vectors is not equal to 0, then some Vj is a linear combination of the other vectors. Okay, this is not correctly written, guys. Very important observation. Theorem 7 is not saying that every vector in a linearly dependent set is a linear combination of the preceding vectors. That's what it simply means. You just to have, suppose I had vectors, say v1, v2, v3, v4, v5, v6. I had 6 vectors in the set S. And I say my S is linearly dependent because I found that v3 can be written as v6 minus v1. That's it. Clearly, I could find v3 could be written as a linear combination of v1 and v6. I'm done. I don't have to worry if it is not. It has no relationship with the v3, v4, v5, or v2. Or I could also say, hey, I find that v2 can be written as minus v1. Done. Even if at least two vectors have some kind of a relationship, that's done deal for a linear dependence relationship. Let's look at an example. If I have two vectors u and v, 3, 1, 0, 1, 6, 0, and we would like to know whether the set spanned by u and v, that means all possible linear combinations. When you see the word spanned, that means you're looking at the span of the set u and v means all possible linear combinations of u and v, alpha u plus beta v. So describe the set which is spanned by u and v, and explain why a vector w is in the span of this u and v if and only if all these three are linearly dependent. Okay. Notice, when you look at the vectors u and v given over here, it's very obvious just by inspection that u can never be written as a linear combination of the vector v. So what does this mean? That u and v are linearly independent. So what does that mean when you look at all possible linear combinations? As done previously, all possible linear combinations will just be a plane in U and V. Okay, now span UV is in the x1, x2 plane with x3 to be 0. Now, if W, so to describe the set spanned by the two vectors, it is going to be a plane in U and V. So basically it's going to be like this. Look at it in a figure. So it's going to be a plane. That's it. All possible U's and V's. Combination of that. That's it. It's a simple plane, guys. Okay. Now, the next is explain why a vector is in the span if and only if they are linearly dependent. If W is a linear combination of U and V, then by Theorem 7, the set of vectors is linearly dependent. Okay, let's look at how it looks like in a graph. Now, if W is in the linear combination of U and V, then clearly W can be written as it will be in the plane. So if this is my plane x1, x2 here, which U and V are some two vectors in x1 and x2, this is what the whole plane will look like. So example 2 generalizes to any set in R3 with U and V linearly independent. The set U and V will be linearly dependent, if and only if W is in the plane spanned by U and V. If it is not in the span of U and V, then W will be somewhere else but not on the plane. Bottom line is this, guys, that if you have a set of vectors linearly dependent, even if two of them are in multiples of each other, we are good to go. Okay, that means linear dependence. Let's look at Theorem 8 and 9. They're very helpful in understanding the concepts, and that's what we'll be just looking at. Let's start with Theorem 8. If a set has more vectors than there are entries in the vectors, then the set is linearly dependent. That is, any set V1 to Vp in Rn is linearly dependent if P is greater than n. So let's take an example. So I have V1, 1, 2, say 1, 2. V2 has -1, 0, and V3 is 0, 1. Okay, say 6 and 1. Now, if I put all of them together in a set, how many vectors I have? 3 vectors. But entries in each vector is 2. So clearly, the set of vectors V1, V2, V3 is linearly dependent. Theorem 9 says if you have a set of vectors which contains the 0 vector, blindfoldly say, hey, that set is linearly dependent. Now I'm going to do some examples which will help you when you do practice problems. These examples have been taken from the book, and they're from the section, the exercise section. Now, determine if the vectors are linearly independent, as there are only 2 vectors. You just look at it and notice this vector -2 can be written as 1 and 4. So clearly, these 2 vectors, V1 and V2, they have nothing in common. So we find that this V1 and V2 are linearly dependent. Let's look at another question here. So we have 4, 4, linearly independent, what did I say? Because one is not a multiple of the other, sorry. Yeah, it's linearly independent. Sorry, guys. Now, let's look at the next question. We have 4 vectors, 4, 4, -1, 3, 2, and 5, 8, and 1. And if I put them in a set, how many vectors I have? Number of vectors, 4. How many entries in each vector? 2. So by Theorem 8, what do we see? That the number of vectors is greater than the number of entries. Hence, these vectors are linearly dependent. Okay, let's look at another set of vectors. Here we have 3 vectors, 0, 0, 2, 0, 5, 8, minus 3, 4, and 1. Now, sometimes it's very obvious by looking at it that they are linearly independent or dependent. Sometimes you have to do the math. So what I'm going to do is I'm going to show you different ways of it. And there come a point when you will just look at the vectors and you say, yeah, I know they're going to be linearly independent. But in this problem, I will show you how they are linearly independent. Now, when you look at these vectors, if they're independent or not, so you can start with, oh, this is vector v1, this is vector v2, and v3. If they're linearly independent, that means the only way the vector equation will be 0 if all the xi's are 0. That's for linear independence. So we write the vector equation, plug in these values 0, 0, 2, 0, 5, 8, and minus 3, 4, 1, and just do some scalar multiplications and vector additions. We get this. Notice what this tells us. Now this is the vector 0, 0, 0. That's what it basically means. So clearly it means from the top x3 is 0 because it is now equality of vectors. So second equation says 5x2 plus 4x3 is 0. x3 is already 0. So 5x2 plus 4 times 0 is 0 according to the equality of vectors. Clearly x2 is 0. In a similar fashion, we get x1 to be 0. So the only way this vector equation is 0 if all the xi's are 0. That's the definition of linear independence. So hence we say the set of vectors are linearly independent. Some of you could have also gone through, oh, let me write the matrix equation, then do the row reduction algorithm, and if all the columns are pivot columns, we are done deal. That's also another way of saying it. Okay, let's continue to another example. We like to know if the columns of the matrix form a linearly independent set. Now, so columns of the matrix, notice each column is a vector, right? I'm trying to see what theorem will make my life simple because each column is a vector. I can think of them as a set of vectors. Think of that way. So every column is a vector. And all 4 columns are 4 vectors in a set. In a set of vectors. It's how you approach the problem, guys. Now, by Theorem 8, the number of vectors, which is 4 here, is strictly greater than the number of entries in the vector, which is 3. Thus, by Theorem 8, the columns of thus by Theorem 8, these vectors are linearly dependent, which basically means, because these vectors are nothing but the columns of the matrix, which means that the columns of the matrix are linearly dependent. That's one way of proving it, because you just have to remember what theorem is the appropriate one which will help you and how you make that connection. That's the whole story. Another way of doing it, is you apply the row reduction algorithm and show that that there is a presence of a free variable. There are many ways, guys. Okay, let's look at another example. Find the values of h, or one value, for which the vectors are linearly dependent. Do you see that here? Now over here, I will have to do some computation. So I'm going to say, okay, I have to find that value which will make it linearly dependent. Be careful. So the first thing we're doing is we're going to write down the vector equation, plug in the vectors for, because there are three of them, we're going to plug these three vectors. And we have to show that this vector equation, there is a non-zero value of x. So because if it is going, now we have to prove that what value of h will make it linearly dependent. In other words, when we are going to apply the row reduction algorithm, and we have to say what will be the scenario, what will be the value for h such that there is going to be a dependence relationship between these xi's. Okay, so here's my vector equation, and we write down the corresponding homogeneous matrix equation, which is given in the next slide. Now we have this matrix equation. Now for a linear dependence relation, what does that mean? That I must have a non-trivial solution, which simply means one free variable. So in order to see if there's a free variable, that we have to get a free variable, what we're going to do is we're going to row reduce the matrix to the echelon form. That's enough, guys, there. In one step, you actually see the presence of a free variable. So you notice what happens. When you apply this row operation, R2 plus 2R1 goes to R2 and R3 minus half R1 goes to R1, I am basically getting a new matrix where I have the presence of a free variable. There are two basic variables and one free variable. Notice there is no condition on h. H can be anything because that's not affecting us at all. So for linear dependence relation, h can be any value or it can take any real number. There is no constraint on h. Okay, let's look at some true-false problems. The first one, if I have four vectors v1 to v4, v1, v2, v3, v4 in R4, and we see that there's a relationship between v3, v1, and v2, then the set of vectors is linearly dependent. True. It is true because we find that there is a relationship between three of them. It doesn't have to be all four. Here, three of them have a relationship. We are done. This is by characterization of your linearly dependent sets. I think that's Theorem 7, I think so. Let's look at that. Previously, yeah. Theorem 7, which says characterization of linearly dependent sets. Okay, so we have got that. The answer is true. They are linearly dependent by Theorem 7. Okay, let's look at the next problem. If v1, v2, v3, v4 are in R4 and one of the vectors v3 is 0, then the set of vectors is linearly dependent. True, by Theorem 9. It says if you have a presence of 0 vector by default, just say, hey, it's linearly dependent. Don't even think about it more. Okay, let's look at another question. Now that's not a true and false. It's more like deep thinking and making connections with things we have learned earlier. It says, how many pivot columns must a 5 by 7 matrix have if its column span R5? Now, when you see the word columns spanning R5, the first thing you should think is, oh, Theorem 4. because that's where spanning comes in. Okay, Theorem 4 of section 1-4. Let me show you the Theorem 4, guys. Okay, what does Theorem 4 says? If A is an m by n matrix, then the following statements are logically equivalent. For either they're all true or false. For each B in Rm, this equation Ax equal to B, the matrix equation, has a solution, or each B in Rm can be written as a linear combination of the columns of A, or the columns of A span Rm. That's what we are getting. You have a matrix A of size m by n, and if the columns of A span Rm, okay, this m and this m have to be are the same, guys. And what does that mean? If the columns of A are spanning Rm, A has a pivot position in every row. Okay, the size of the matrix and the last two statements of Theorem 4 are the key for our answer. Okay, so let's keep that in forefront when we're going to solve this problem. Okay, so according to Theorem 4, columns of this matrix are spanning R5. So let this matrix be, so let A be the matrix, and the size is what? 5 by 7. And we have said that the columns of A span R5. Do you see that here? That 5, this 5, and this 5 are the same. So according to Theorem 4, what does that mean? There has to be a pivot. So by Theorem 4, there is a pivot in every row. Now, how many rows do we have? 5 rows. Now, let's literally write it down. Okay, it's a pivot in every row. I have a 5 by 7 matrix. If it's a pivot, so if it's a 5 by 7, so first row, 4 zeros, first column, 4 zeros. Now, it's a pivot in every row according to Theorem 4. Then second row, 3 zeros. Fourth row, or third row, 2 zeros. Fourth row, so remember it's a 5 by 7, so I have 5 rows. 1, 2, 3, 4, 5. And then last one will have, it has a pivot in every row. Pivot means a non-zero entry in a non-zero row. Okay, so now it has 5 rows, but how many columns? 7 columns. So the rest, we don't care what the values are, but there are going to be 7 more of them. That means that this was the 5th one, 6th and 7th. That's how it is going to be. That's how the matrix will look like. So how many pivot columns do we have, guys, now? You have the matrix in front of you. 1, 2, 3, 4, 5. So according to the question, how many pivot columns? We will have 5 pivot columns. So it's very important, guys, that your previous sections, they have to be continuously practiced and practiced, because as we keep on adding more and more concepts, I will be going back to all of these sections and using their theory to prove the results of the future sections as well as the section which we are doing today. Okay. So we have done a lot of examples, theory. It's time for you guys to practice. So I would like you guys to practice a bunch of these problems. And they're very, very important. Many of them are computation. Please make sure you are practicing the computation, specifically writing down the solution sets and seeing how whether the sets are linearly dependent, independent, all sorts of things. Okay. Work hard, very, very important. As I said a few minutes earlier, we will be utilizing a lot of the concepts we have learned in previous sections. Thank you.